One of the earliest things that you could probably do in embedded systems to really make sure that your board is up and alive and be able to start interacting with your system is to be able to configure UART. UART is a way for you with the launch pads to be able to communicate with your board, and it's really valuable for certain debugging aspects, even though you have a full debugging suite built into Code Composer. But it also provides you a sort of interface for you to control your code and see certain things without needing to actually stop the processor and inspect the registers. It's really powerful and probably one of the first things you should try to get working outside of blinking an LED. So what I want to do is I want to show you how I would actually approach this and get the UART peripheral running without really needing to know too much about what UART under the hood actually is. So to get started, I'm going to go to the Resource Explorer. Now, unfortunately, because it remembers what I did last time, if I go all the way back to the top, I'm going to show you what you could go through. So you could say detect my board, and it found that I have the G2. So with the G2, I can go through here and pick the G2553, and I can go to the register level examples. If I scroll down, sorry for some of the flickering there, I'm still trying to figure out why that's a issue. What I can go and do is use the Universal Serial Control Interface, I think is what it's called, or Universal Serial Communication Interface, or USCI. If you look down here, we actually have an example for 9600 baud UART. What I'm going to do is I'm going to click on that, just double check to make sure that it's what I want, and it is. Cool. And I'm actually just going to go over here and hit import, and I'm going to pick the G2553. And I'm going to hit apply, and it'll actually create a project for me in my workspace. So if I go over here to my project explorer and I actually click on the code, what will actually happen is it'll open it up. I'm actually going to close the resource explorer here. So don't at me with how I have my thing configured. This is literally stock Code Composer. So I've done nothing. I think it's tapping into the fact that I have night mode turned on. But here's the idea behind UART. Is essentially it is a 2-pin communication between your target and the embedded system or your microcontroller, and there's a couple things that you need to make sure is configured. You may see in the demo or in the diagram up here, it's saying 9600. So 9600 is the baud rate. Think of it as like a symbol rate or character rate, but in our case, our symbols are bits. So think of it as 9600 bits per second. We need to know that because one of the things you'll talk about in class is how we don't share a clock signal across the two devices talking. So things like the bit rate is very important to be able to effectively know what's being said. The 8N1 is other configuration things that, we'll worry about later in class. And I'll show you how to set them up, or I'll show you what they mean just in the briefest amount in a second when we go over to look at the thing actually physically working. So here's what we're going to do is this is a full working example. In the beginning up here, what it's doing is configuring some basics with the microcontroller. It's stopping the watchdog timer, setting our clocks and everything like that. And then what it's doing is it's picking our 2 pins for the RX and TX. Now in the data sheet, if you look at the pinout for the pinout map for this processor, the G2, there are only 2 pins that really support hardware UART, pins 1.1 and 1.2, and on your launch pad, they're indicated as RxD and TXD. We're going to use those. We're also going to tell the peripheral that controls the UART interface, hey, I need you to use the submain clock, and we're going to set some dividers here to set the right baud rate and what type of modulation we want. And this example also uses interrupts. So essentially what this is going to do is do all of our configuration and then sit here and basically say enable all the interrupts, I'm going to go to sleep now. So the only time that this code will actually fire off, and I'll show you this with a breakpoint pretty soon here, is when we receive something from the other device. When it does, it'll wake up and basically say, are you ready to transfer data yet? And once it's ready, it'll actually transmit whatever it receives. So you know what? Let's just program this thing and let's see what we can find out about it. So all I did was I found the example. I'm going to go up here to my debug environment. Now you can build and go into the normal environment outside of using the debugger, but this sets up a lot of cool resources for us. If you get a warning about the ultra low power advisor, I advise you to keep this on, meaning that don't click this do not show message again. Just hit proceed. That's really useful for low power configurations and trying to figure out the best way possible to efficiently run your code. Now there's a few things that pop up. I've used this a couple times, so maybe some things might look different. So essentially, in the top left, you have the files and the stacks that are being used. You have on the right here a couple of main things. You've got the variables tab, which you can use to keep track of any local variables we're using. And it's kind of interesting. If you take a look at what our code is doing, there's actually no variables being tracked. So this is going to be pretty empty. You can also do expressions that you're looking for as well. You can add custom things. But what I really care about for this demo is I'm going to keep track of my registers. This is where things happen. This is where the magic happens. So in here, I'm able to actually see all of the register contents whenever the processor is stopped. So right now, we've just programmed the processor, and it is halting right now at the first line of code. So for example, if I wanted to look at the watchdog timer, this line of code that's highlighted on line 72 is basically saying I want to turn it off. So if I go to the watchdog timer, you can see this watchdog control register in all of its little, sub, areas. What I'm going to do here is in the debug menu, we have a couple options. You can just hit go, and it'll just run the code, which is great. You can stop it, and it'll basically bring you back to the editing menu, which is basically terminating the entire debug session. What you can also do is step through your code. So you can do things like if you call a function, for example, you can step into it. You can also step over a function, basically saying run the code, move to the next line, and you can do also step until you return. So what I'm going to do here is I'm just going to use step into. So first things first, I'm going to move this, and this is effectively the processor moving forward. I don't want to necessarily say one clock cycle, but one line of code. So if I hit next, look what happens. My contents changed over here. Now, does this really mean anything for you all? Probably not at this point. But what I'm showing you here is that with the debug environment, with looking at the registers, we can now actually see what's changing and track things. And in fact, what's kind of cool is if you wanted to go in here and change that back, you can. I'm going to keep it 1 so that way we actually, maintain some stuff, maintain what it's doing. So what I want to do here is I could step through this whole thing and walk through and everything like that. But instead, I can use something called a breakpoint. Now, you need to use breakpoints if you're using interrupts. So what I want to do is I want to wait until we actually do something down here, which is I'm ready to transmit something that I receive. So I'm going to double click, and it's going to put a breakpoint. So what I can do here now is hit resume. And now my processor is running. No matter what, these registers are never going to update over here because it has to halt so that the debugger and the emulator on your board can actually inspect those registers and give you the values. So right now the code is actually running. It did all of its configurations and it's waiting for something. So you know what? Let's send it something. I'm going to move this out of the way here, over here because it doesn't want to leave. So here's what I'm going to do. Is I'm going to change this. So all of this stuff right here is from Scopy. And it's that ADALM thing that you all had. So what I'm going to do here is I'm going to go back to my settings and I'm going to change my delay to -31 or 32 or something to clear the screen. I'll have a whole video up on how to use this, but essentially here's what I want to show you. I'm going to use Scopy to send the letter, pick a letter R. So what I've done here is I'm using Scopy's pattern generator to generate a UART packet, effectively, like a UART string or a UART string of bits. And it has the start bits, the stop bits, and all the content. It's showing you what it's going to actually send. And I've configured it such that one of the pins is actually going to go onto the receive, and one of the other pins is listening to transmit. So on the window on the right here, I have what I'm going to send to the MSP430, and on the left here is I have TXD, which is going to be basically what are we receiving. And I've told it already that I want to listen out for a UART type protocol, and I want you to try and decode it. Remember that baud rate thing? We need those information. So that 9600, we need that. The data bits is the 8, and N and 1 are all about the parity and the stop bits. So if we go back to the example real fast, when it's talking about all of these settings, 9600, 8, and 1, it's talking about the baud rate, the data bits, the parity, and the stop bits. So let's send this the letter R. If this is truly an echo system, what I should expect back is the letter R. Now remember, when you're doing anything in your embedded system, you may say, well, the letter R looks a little weird here. That's because it's being sent in binary. We're using the ASCII representation for R, which means it's hex. I can change the look of this, I believe. But I believe R is like hex 40 something or 50 something. So 5 something. So that's what we should expect to see back. So here's what I'm going to do. Right now, my code is waiting. You can see right now the last instruction I was highlighting was line 73. It's now waiting for me to send something and hop into that interrupt. So you know what? Let's give it something to interrupt it. So I'm going to send it. It looks like nothing happened, but if I come back to my code, all of a sudden, it's stopped here. So my debugger has stopped right here, and I hate sometimes how it highlights that because it makes it very difficult to actually see what's happening. But this is the line of code we're stopped at. What does that mean, and what can we look at? So here's what I'm going to do. You know what? Let's see what data it just captured. If we're correct, if we've done everything right, we should see ASCII R, which is like 50-something, show up. So if I go over and inspect this register, the UCA0 RXBUF buffer, so the receive buffer, if I go into USCII A UART mode, and I go down and I see the RX buffer, I see 52. Great. That's a really good thing, because that means it received our R. Now, if I step forward by 1, what's going to happen, or if I step over, it will throw what's in the receive buffer into the transmit buffer. As you can see here, it just it threw it into the transmit buffer. Then if I hit resume and I come back over here, well, my logic analyzer found something. And if I zoom in, it's our letter R. So what the debugger is letting you do is actually put in these debug points or these breakpoints to let you see what's happening. So just to show you I'm not, creating something out of thin air, let me send another R packet, pause the debugger, and let me show you that I'm really actually able to, that you're sending what's in the receive buffer. I'm going to change this. What if I wanted the letter S? Let me make it 53, so I hit enter. Now when I go to the next step, let's see if it actually listened. It didn't. Great. Sometimes it does change, sometimes it doesn't. But I still get R. If I send an S and I remove my debug point you can do it by double clicking. Now whenever it receives the interrupt, it's just going to run. Hey, look, I got an S. If I wanted to send T, I can send T. If I wanted to, let's send this out. If I wanted to send testing, it shows you what the UART package should look like. And if I send it, hey, look, byte by byte, we got testing. Well, I mean, this one's a little zoomed out, but testing. So this is where this stuff is really cool. And you've effectively now created a way to access your microcontroller and send it information. Let's say we wanted to mess with this. I know this is going to end up being probably closer to 15 or 20 minutes, but I just wanted to show you all this. So what if I wanted to experiment with this? What if instead of sending back, for example, whatever I receive, what if I wanted to send the next ASCII character? Well, that's easy. I can just take whatever I receive in my binary representation or my byte representation, add 1 to it. So now I've just modified the code, come up here to debug, and say, sure, I need to save my resources, the low power thing will come up, hit proceed. Again, it might get annoying, but please, I recommend keeping it up. So we've programmed it, it's loading the program in, and now we're in. I'm not going to put a breakpoint in, but all I've done is I've changed it to say +1. So I'm going to run my code. I'm going to come over here, and now if I type in, let's say, ABC, I should hopefully receive back BCD. And guess what? We did. It sent back BCD. So using UART really is not all that complicated, and I didn't need to really explain what's actually happening. But I will put up a video that goes a little bit more in detail and actually show you the oscilloscope side of things that, you actually can see what's happening. In terms of using this data usefully, what if instead if I have and watch me embarrass myself as I completely mess up a system here, is one of the ways that you could possibly do this is you could echo back txbuff if you wanted. You can also use this information and set something like a global variable, or you could return it back. So you could have a variable that you call and you return the returned character back and you check what it is. A good exercise that I recommend you all try to do, and it's really not that hard, is control your LEDs on your board using UART. Maybe if you send the character 1, it turns the red LED on, and if you send a 0, it turns the red LED off. Or if you have 2 LEDs on your board, for example, what if you sent capital R for turning it on, a lowercase r for turning it off for the red LED, and a capital G for turning on the green LED, and the capital R and a lowercase g for turning it off. I mean, there's a lot of stuff you can do, but if you can try to get through and understand roughly how this works, you've now unlocked a way to successfully communicate with your board. Also, this is a small little plug for saying, yeah, that ADALM thing that you have that you all probably didn't like from last year, it's a pretty cool device to be able to figure out what your board is doing, because without it, I wouldn't really be able to know. I might be able to use the back channel UART on the thing, but once we start talking about, doing, let's say, PWM or things like that, it becomes very, very useful to be able to see what's going on. So with that, just as a recap, what we did was we went into the Resource Explorer. So let me stop my debug session here. By the way, before I hit the recap, one last thing. I promise one last thing. This code is still running on that board. I haven't, just because I hit terminate means that all it does is it stops the debugging session. But this board right now is running. So it's still running my code. So if I send 1, 2, 3, I should get back 2, 3, 4. As we see here. So my code is running on the processor even though the debug session has stopped. So that's just something I wanted to point out. I think a lot of people feel like their code only can run while debugging, and that's not the case. You are actually programming this thing. So just as a recap, what we did was from the Getting Started page, we went to the Resource Explorer, and we found a project that we wanted, the UART one, and we imported it into the Project Explorer, and we literally just ran it. And this is a way to communicate with your device. We showed the debug, the debug panel to start looking a little bit about like register access and see a little more in depth about what each one of these commands are doing. And we were able to actually show communication back and forth, not just an echo, but we even modified it to say, add 1 or add 0 or add 2 or, start unlocking a lot of cool things that you could do with this UART connection.